Good morning and good afternoon. Thank you for attending the Introduction to UCIe webinar. Today's webinar is presented by Dr. Debendra Das Sharma, UCIe Consortium Chair. And as a reminder, we will have a Q&A session at the end of the presentation. Please share your questions in the Q&A chat box, and we will address your questions during that time. Now I will hand it off to Debendra to begin the webinar.
Thank you, Elsa. Greetings, everybody. I'm really excited to talk about Universal Chiplet Interconnect Express, abbreviated as UCIe. This is the disclaimer that you can read. Now, here is the agenda for today. We will start with an introduction to UCIe Consortium as an organization. Then we will talk about the opportunities and challenges that we have with on-package interconnects. Next, we will delve into UCIe technology and see how this open standard is addressing the needs for chiplets. Finally, we will conclude and then have a question and answer session that will be moderated by my colleague, Gerald Fastas. UCIe Consortium was formed in March of 2022. We incorporated in July of 2022. We have 100+ member companies. There are 12 board members that are listed here. Leaders in semiconductor, packaging, IP, foundry, systems, and cloud service providers have joined together to drive the UCIe-based open chiplet ecosystem. Now, UCIe Consortium is an open organization, so we do invite all the interested companies and institutions that have not joined us to join us either at the contributed or the adopter level. Both contributors and adopters have access to the final specifications. They both have they can implement with IP protections as outlined in the agreements. They can attend corporation trade shows or other industry events. Now, the contributor members do participate in the technical work groups and influence the direction of the technology. They also have access to the intermediate, the dot level specifications leading to the final specification. And they're eligible to stand in election to get to the promoter class or board every year when the term of half of the board members expires or completes. Now we will look at the opportunities that exist with chiplets, as well as the challenges that we have to overcome in order to realize the vision of an open ecosystem for chiplets. Gordon Moore had predicted the day of reckoning in the same seminal paper where he postulated Moore's law in 1965. Today, if you look across the entire industry, mainstream products, mainstream CPUs, mainstream devices are being designed out of smaller chiplets using proprietary mechanisms. So we are already at a major inflection point in the industry, and UCIe is bringing the industry together in order to establish an open plug-and-play chiplet ecosystem. Now, let's talk about the motivation for on-package integration of chiplets. There are many drivers for on-package chiplets. Now, as the die size increases to meet the growing performance demands, designs are running up against the die reticle limit. Examples include multi-core CPUs, where the core count is in the hundreds of cores, or very large fan-out switches. Now, even when a die can fit within the reticle limit, multiple smaller dies connected in a package may be preferable for yield optimization, as well as for reuse across the multiple market segments. On-package connectivity of identical dies, these are what we call scale-up applications, are already there, and that can be enabled by an open chiplet ecosystem. The other aspect has to deal with the IP porting cost. Here is a study done by IEEE, and as you can see, the IP porting costs are exploding exponentially. Even if you didn't change anything, just the porting costs are going up with the increase or with the advances in the process node, as you can see here. Now, the good news here is that we don't have to port all the IPs, especially whose functionality does not change by putting them in a chiplet and reusing them. Now with the die reuse, we also get the time to market advantage. Another motivation for on-package integration is to lower the overall portfolio cost, both from a product as well as from a project point of view. Now, for example, compute cores can be implemented in an advanced process node to deliver leadership power efficient performance, of course, at a higher cost. Things like memory controller, IO controller functionality, they can be reused from a design that already has been deployed, maybe in an established N-1 or N-2 process node. Now, this kind of partitioning also results in smaller dies, which results in better yields. The other advantage of this chiplet integration on package is that it enables a customer to make different trade-offs for different market segments by basically mixing and matching the dies that are available. For example, one can choose different number of compute dies or chiplets, different amounts of on-package memory, different numbers or types of accelerators or number of IO dies, depending on the need of a given segment. And one does not need to go and do a specific die design that meets the needs of a given segment. So you can just do them by mixing and matching the chiplets. And these result in lowering your overall product cost. And they can also enable us to provide custom solutions by doing this mix and match. So done properly, die-to-die interconnects, they offer the compelling power and performance characteristics. If they do that, then we can use them to build a truly open chiplet ecosystem. And I'm confident this is a game changer for the entire industry. Now, there are four major things to consider for an interoperable chiplet ecosystem. All aspects need to be addressed to drive a truly open, interoperable chiplet ecosystem. And I'll go from the bottom to the top. Die-to-die IO, this is the physical layer, this is the electrical layer stuff. It gets a lot of attention. This is necessary, but it is not sufficient. If you just specify a die-to-die IO, that's like giving somebody a SerDes on an off-package interconnect. They're not going to know what to do with it. So, but then on this, like I said, this is a very important aspect. We do address it fully. And things like, bump arrangement characteristics, electrical characteristics, thermal characteristics, what is the channel characteristics of the substrate or the interposer, what is the length budget you provide, how many picojoule per bit you have, what is the bit error rate, things like reset, clocking, initialization, frequency of data transfer, importantly, test, repair. And in general, we just need to have a technology transition story as the underlying technology moves forward. Next comes the die-to-die protocols. You need a protocol to run on that physical layer. So this is effectively, taking your link layer and any other upper transaction layers that are there. Examples of transactions that you may want to run are things like PCI Express, CXL, or any other proprietary kind of protocol or streaming protocol is what we call. You can also have a raw mode, and we will see pictures of that, as we go along in this talk. Next comes the application layer. This is the SoC construction. So you need to address things like reset, initialization, register accesses, security, and then you also have the chiplet form factor. What is the die size? Where are the bumps located? What's the power delivery mechanism? All of these things, they need to be addressed completely and holistically in order to drive a true open plug and play ecosystem. Now, we need to think of the same software, the same IP, and then the same subsystem being applied from a node level to a package level to an SoC level as shown here. This will enable us to build scalable solutions. This will offer us the economies of scale, time to market advantage, and above all, a seamless user experience. So let's take, for example, we can see a world where you have this multi-socket server system where you got multiple CPUs, you got a bunch of PCIe CXL cards, got memory attached on the board. Now we can integrate some of those on the package, as you can see here, on package memory, the CPUs, some IO tiles, and then you got accelerator or accelerators being connected on a package. So this is where some of these components on the board move to on the package, and then if some of them are for a smaller die for some segments, then you can even move some of this functionality from here to one of the given dies for an on-die kind of integration. So you want to be able to fungibly move things across depending on the segments that we serve in. And there can be cases where we will move some things from on die as the die sizes are increasing, as we talked about, split them and make them multiple dies, like we talked about in the introduction part, right? So that this movement can go in either direction. So, examples of things that can move back and forth are, for example, NIC, right? Where do you integrate the NIC? Is it off package? Is it on package? Or do you want to make it on die? Things same way with accelerators, some accelerators, right? Are they off package? If it is big, you want it off package. If it is reasonably within your power profile, you can be on package. And if it is really small, you can move them on die. So we need to think of this world as, having to seamlessly deploy solutions from the SoC level to the package level to the node level. And this is where, having the same software, IP, subsystem in order to build the scalable solutions offers us the economies of scale, because it's just a matter of putting things to the right place. And this gives the time to market advantage. And most importantly, it gives the users the seamless experience. And this is an important aspect where we have been very successful at open slot innovations at the board level. We want to make sure that those kind of innovations migrate to the package level in order to address multiple market segments and multiple usages. And we'll see that UCIe is targeted towards those things. Now we will delve into the details of UCIe as a technology. Now, before we get into the details, let's talk about 4 of the essential guiding principles of UCIe. Some of us that are driving UCIe, we have decades of experience in driving very successful industry standards like PCI Express, USB, recently CXL, which are ubiquitous interconnects in spreading across the entire compute continuum. So the guiding principles that are listed here are from the best practices that we have deployed in these standards and we are leveraging for UCIe. First and foremost, we must support an open ecosystem with plug and play. Now, what that means is if you decide your chiplet will have a plug and play interconnect to hook up to another chiplet you may not even know about at that point, it will still work. Now, we will allow people to build their own proprietary solutions, scale-up kind of solutions that we talked about with UCIe, but they can also deploy some open ports. Now, let's look at PCI Express as an example in the previous slide, where people deploy PCIe or CXL stack on the PCIe 5 for the open slot, but also PCI Express 5 got deployed for building the symmetric cache coherency protocols on top of PCIe 5 to do this scale up 2-socket, 4-socket systems. Both are supported. This will follow the similar model where you're going to have an open slot if you want to plug and play with anybody, and that plug and play can work. Somebody can design a chiplet 10 years from now, it will still interoperate, or you can use it for building your own scale-up solutions. Second is backward compatible evolution within the same form factor. This is what we follow very rigorously in all of these other standards, PCIe, USB, CXL, and it has been critical to ensuring their success over the decades. Backwards compatibility ensures that people can innovate on the next generation of UCIe specification when that comes out without worrying about exactly when the rest of the ecosystem will catch up, because you are going to interoperate with whoever is there, using the baseline, which will be 1.0. If you're within that form factor, it also helps with investment protection, and it helps with the sustainability cost due to reuse. So for example, today, if you look at the board level, a 20-year-old PCIe Gen 1 card, it still works on a PCIe Gen 5 based system, latest system today, assuming, of course, the functionality of the Gen 1 card is sufficient, right? So you want to have that model where things can just plug and play anytime, with anything being designed in the future or anything that has been designed in the past. Third is the quantitative stuff, right? We have to have the best power, the best performance, and the best cost metrics that one can deploy in their designs. And what this does is it offers a compelling value proposition for the designers, so that they can partition their large monolithic designs to chiplets. Because when you have something on die, you are getting these metrics are very good. So you need to come very close to that. And also it offers them value when they migrate things from onboard to on package, because they're getting tremendous amount of savings in these metrics of power, performance, and cost. Now, we need to also make sure that these metrics are applicable across the different and sometimes competing demand across the different flavors of compute, so that it's ubiquitous, right? So you need to come with scalable offerings like PCI Express does, so that way you can apply it from the handheld all the way through the supercomputers. Now, while challenging, this will create a virtuous cycle of innovation due to the large number of applications that UCIe will be involved in solving. And last but not the least, we must continuously innovate to meet the needs of the evolving compute continuum. Now, one of the things that I have learned over the past 20 plus years since the beginning of PCI Express is that you have to anticipate and you have to meet and exceed the needs of the computing demands as the compute segment itself goes through the changes, in order to make sure that the interconnect that you're defining and you're driving continues to stay as a ubiquitous interconnect as this compute continuum evolves. So bottom line is, again, we are leveraging our decades of experience. We are bringing that to bear to UCIe to drive an open ecosystem for the entire industry to innovate on. Now let's talk about some of the motivation for on-package integration of chiplets. There is a white paper on the UCIe website that goes through these aspects in more detail. You can go download those. Now, just to summarize, we talked about a lot of the designs are hitting the theoretical limits as the processing demand continues to be insatiable. Now, constructing SoC out of smaller dies in a scale-up manner is being deployed today to overcome that. With die reuse, we can also get time to market advantages as well as overall lower cost to solution. Now, the cost advantages comes from, like we talked about, deploying optimal process nodes for the functionality that you're targeting, improved yield with smaller dies, cost savings from not having to port IPs that are already being deployed, overall SKU cost reduction due to mix and match of chiplets to exactly meet the need of the customers, where the system on the package can be deployed. And one can also offer bespoke or custom solutions by adding or substituting dies as needed. So our vision is that we want to have like an open platform with heterogeneous integration. One can assemble chiplets from different nodes, different fabs, different design houses that can be assembled anywhere. So in this example, you got a C of course, you got some customer IP, customized chiplets, you got memory connected. You can have all of these being integrated on the package effectively. What we are doing at the board level with open industry standards like PCIe, CXL, USB, we want to make sure that those get done at the package level, an open ecosystem that we want to drive. Now, the purpose of UCIe is, of course, to offer this open platform with standardized interfaces so that the industry will align and it will keep on innovating. Now, with UCIe, as you will see, we are offering compelling cost, power, and performance characteristics. And I'm confident this is a game changer for the entire industry. Now, UCIe has been architected and specified ground up to deliver the best key performance indicators or KPIs. The key performance indicators or KPIs are listed here on the left side, which, things like bandwidth density, that's an important indicator, KPI, linear density, which basically says how much of source line of the die you're taking, area density, how much area on the chip you're taking. So these are dictated by the data rate and bump pitch, very important. Energy efficiency is extremely important. But most importantly, we want that energy to be scalable. In other words, if I consume 10% of the bandwidth, I should be burning 10% of the power. And in order to do that, we basically need to make sure that there is low idle power, but most importantly, low entry and exit time. And we will see the metrics as we go through the tables in a later slide. Latency is extremely important. These are, again, end-to-end holistic latency, not just the PHY, but everything else. Channel reach is important. The technology transitions are important. Frequency is important. Bit error rate is important because it also, and how you use those to build a reliable and available solution, that's very important. And cost is an important metric. Now, in order to ensure the wide adoption, we have defined a full stack leveraging existing software and IPs that cover a wide range of usages. So things migrating across different process nodes, packaging options, power delivery, cooling, repair strategy, things like debug, very important, controllability and observability. Most importantly, we are having a very broad industry support and open ecosystem, and we are taking the learnings from our standards effort and driving this technology so that it becomes a truly ubiquitous technology across the industry. And we will all innovate based on UCIe. Now, UCIe 1.0 specification was released in March of 2022 when we started the consortium. It reflects our experience and learnings from implementing die-to-die interconnects for about a decade in volume Intel CPU products. Now the UCIe Consortium owns the UCIe specification and is innovating on the evolution of the specification. UCIe is a layered protocol. We have a super optimized PHY layer that helps us to deliver the compelling KPIs that we talked about. We support both standard package, which is 2D, as well as advanced package, which we refer to as 2.5D. Each layer has its own architected set of configuration register for things like control, things like reporting capability, reporting status, runtime status. So those are all architected within each and every one of the layers. Now the PHY layer, it defines the things like circuits, the channel characteristics, clocking, sideband mechanism, bump placement. It also defines things like frequencies of operation, lane repair, lane reversal, scrambling, descrambling, link training, right? All of these aspects are properly specified to ensure interoperability. And these are very well specified. None of these are left for imagination, right? So to speak, you specify things really well so that you can work with somebody that you have not seen, right? Their chiplets, and that could happen a few years down the road. Now, the internal interface to the physical layer or the upper layer is this raw die-to-die interface, RDI for short. Now, we also have defined a die-to-die adapter layer, which is known as D2D adapter for short. This is basically the equivalent of link layer for other protocols. It is responsible for reliable delivery of information. It also defines the arbitration and multiplexing among different protocols if the die supports multiple protocols like CXL. The die-to-die adapter defines CRC and replay mechanism for reliable transmission if that is needed. It also does all the power management stuff, configuration registers, parameter negotiation. So all of those things are built in here. And the die-to-die adapter interfaces with the upper protocol layer using a fleet-aware die-to-die interface, or FDI for short. Now, the scope of the UCIe specification is the physical layer, including the bumps, bump map, form factor, through the physical layer, raw die-to-die interface, the die-to-die RDI interface, die-to-die adapter, and the FDI interface, all the way from there to here. That's the scope of UCIe specification. Now, some applications, they may bypass this die-to-die adapter altogether and just use the link in the raw mode. So in that raw mode, you're basically going directly into the RDI interface. And that might make sense for example, if you want to have a SerDes that has its own protocol, you just are using the UCIe. So you have a separate SerDes die, you're just using UCIe to pass the raw bits because your underlying protocol that is running over that SerDes will have its own reliability and other mechanisms. Now, for the protocols that are explicitly mapped onto UCIe, those are PCIe and CXL. We also support all the other protocols as a streaming protocol, and multiple protocols can be multiplexed on UCIe. With PCIe and CXL, those are the volume attach for plug and play. So, things like the generic IO attach, whether it is a NIC, whether it is any kind of the memory kind of device can be satisfied through CXL.io or PCIe. The memory kind of attach is satisfied through CXL.mem. Accelerator may be just IO, but it could also include the caching semantics of CXL, the memory semantics of CXL, in addition to the IO semantics. Now, another key aspect of UCIe is that we support what we call streaming protocols. This is the and we'll see some specific examples of streaming protocols today. These are for things like scale-up systems. For example, if you are building a CPU from multiple dies, you are building a GPU or a switch, basically scale-up kind of things, from building larger components out of smaller chiplets, scale-up protocols. And the protocol can be anything. It can be AXI, it can be CHI, it can be SFI, CPI. Pick your favorite protocol there. It will run, and we have the provision for either going the raw die to die, or you can just come through the FDI interface and take advantage of the reliable delivery mechanism. We have also defined configuration register in each layer, and we have defined mechanisms for existing software to run seamlessly. We have a well-defined compliance mechanism, and we are working through how to deploy it when chiplets come for testing. The RDI and FDI interfaces that we have defined are done so that you can buy off-the-shelf IPs and deploy them. For example, you can buy the physical layer from somebody and then do the die-to-die adapter yourself, or you can do mix and match, and that's where the properly defined interfaces helps. Now, in summary, UCIe is a well-defined specification in the same way PCI Express, CXL are, in order to ensure a true plug-and-play interoperable ecosystem. This is the start of a multi-decade journey. We are going to evolve this specification. We are going to incorporate new usage models. We will be working on 3D integration, things like that. The consortium will innovate on other aspects, and we have seen this time and again in the other consortia that we drive, and UCIe is headed in that direction. Now let's talk about packaging. Now, from a packaging point of view, the same UCIe 1.0 specification supports two types of packages: standard package and advanced package. Now, the standard package is also referred to as 2D packaging. Here you have the same bumps, typically between 100 to 130 micron minimum distance apart. Some of them can go through and connect to other UCIe components, and some of them may escape the package substrate and go out as package pins, eventually onto the board. So naturally, these are cost effective and support longer trace lengths up to 25 millimeter. Now, the second type is advanced package, also referred to as 2.5D package. Here, the distance is very short. Importantly, these are micro bumps that are spaced very tight between 25 to 55 micron, according to the specification, to deliver more bandwidth in the same source line. So you're basically packing a lot of pins in the same area. As a result, you've got very high power density. And since this distance is also small, the power consumption is lower than 2D. And there are different solutions available from different foundry and OSAT. OSAT stands for outsourced assembly and test. UCIe works across all of them. There are three examples given here. This is EMIB example from Intel. This is CoWoS example from TSMC. And this is Focus example from ASE. So three examples. There are more, but we just picked three as representative samples. Now, the vision of UCIe is that dies can be manufactured anywhere and assembled anywhere. One can mix 2D and 2.5D in the same package. We want to provide the maximum flexibility for the SoC or package designer. So what we are targeting is that we want to build a truly open ecosystem. Now, UCIe is architected ground up with process portability in mind. Now, all the circuit components can be built with common digital and analog structures that are widely available. We specify the bump out. This is an example. These are some examples given here for that can be used for interoperability. That's why it is needed. We support die rotation, die mirroring, and this is like a sample bump out for the unstacked case. You can stack 2 of them in the standard case. That way you get less soar line. This is an advanced package bump out. And the picture here on the right, it shows how different bump pitches can interoperate because of the fixed beachfront requirement that we have. So for example, you have one side that is 55 micron talking to 55 micron. Well, this is how you'd connect. If you have 55 micron and 45 micron chiplets, then what happens is that since they have the same soar line, they just have different depths, but you can connect them the same way. So basically, this is done so that your routing is easy. Now let's delve into the details of the physical layer. The physical layer deals with things as a module. One unit is one module. So you can have a single module. You can have 2 modules as shown here, or you can have 4 modules as shown here, combined to form one link. These are all single-ended signals for the data. So represented as N, if it is, if it is a standard package, N is 16. If it is advanced package, N is 64. So for every module, it is 16 lanes in one direction, 16 lanes in the other direction, transmit 16 lanes, receive 16 lanes, or 64 lanes if it is advanced package. And we have 1 lane for valid. We have a differential forwarded clock, differential pair. We have 1 lane single-ended for calibration stuff like tracking. Lane reversal is supported on the transmit side. Reliability is offered through spare lanes in the advanced package. So even though N equal to 64, you got a couple more extra lanes that you can use to, if some lane goes bad, you can substitute, and that applies to for not just data, but for all the other entities within that link. For the standard package, it is degradation. So 16 lane becomes 8 lanes. Again, this is similar to what happens with the bumps on external interconnects. We support a range of frequencies, 4 gigahertz, 8 gigahertz, 12 gigahertz, 16, 24, 32. Anytime you support a data rate, you have to support all the lower data rates. So for example, if you support 16, you must support 4, 8, and 12 also in addition to 16. So this ensures that you can interoperate with somebody else. Somebody might be designing, let's say, to 32 gig, and let's say you have designed to 16 gig. Well, the one that has designed to 32 gig will support 4, 8, 12, 16, 24, and 32, and you are supporting 4, 8, and 16, so you are going to run the link at 16 gig. So that ensures interoperability. The bandwidth per module, you get 64. This is for every module, right? 64 gigabytes per second for standard, and 256 gigabytes per second for the advanced. So this is equivalent to this is equivalent to a PCIe Gen 6 bandwidth, right? Gen 7 bandwidth. Now, 2 modules gets twice that, 4 module gets 4 times that. Now, for the sideband, it is always on. There are 2 lanes for every direction. They run at 800 megahertz. The 2 lanes are data, clock, and this is used for things like training, debug, management, etc. And it leverages the depopulated bumps to ensure that we are not adding to the soar line. And valid is used for effective dynamic power management that we will see. Now, the die-to-die adapter is responsible for the packetization. So what it does is it takes the existing bits, it adds flit header, and it adds a CRC. There are 2 broad sizes supported, 68-byte flit and 256-byte flit. Within 256-byte, there are 2 flavors. One of them is a latency optimized version because you can get the CRC in 128 bytes and process it. The other one, you have to wait till the end. The flit header has things like, protocol ID, credit, flit management, like, ACK, NAC, if you got a NAC, what is the sequence number, all of those things, right? Things that you need for reliable transmission. And CRC, it covers the 128-byte payload. The smaller payloads get 0 extended. It basically provides triple bit flip detection guarantees. There is a replay if the CRC fails. And the spec is so detailed that we even provide a sample RTL code. Of course, you can do your own pipeline design and all of that, but there is a sample RTL code that you can compare against in the specification. So we take everything and we specify it so that there is less room for error. Let's put it in that way. Now let's look at the usage model supported by UCIe. UCIe supports two broad usage models. The first one is package level integration to deliver power efficient and cost effective performance as shown in the figure here. Now, recall that components that were attached at the board level, such as memory, accelerators, networking devices, all of those we said we want to move into the package, right? That's what you see here. The things like even modem, all of those things, right? RF, those things come on the package. So you got mix and match dies from different process nodes, connected using UCIe. For example, the processors here can be in the most advanced node and connect using a symmetric coherency protocol mapped on UCIe through FDI, either as 2.2D or 2.5D, standard package or advanced package, depending on the need. Memory, for example, can be connected using CXL.mem protocol that is mapped on UCIe through the FDI, the flit-aware die-to-die interface, using advanced packaging so that you get high bandwidth, low latency, low power, all of that. Accelerators can be a mix of different process nodes. Some may be established, some may be more advanced node, depending on the need. And they can use PCIe, CXL, or streaming protocols. And we'll see more examples of this on UCIe through FDI. Things like modem, RF can use, they will use optimal analog process technologies, and they can use raw mode, RDI, connected through UCIe 5 to communicate. But what happens is that this flexibility, it enables UCIe to work across all the segments of compute, right? From handheld, client, server, workstation, communication, HPC, automotive, IoT, etc. The next two slides that I'm going to present are from our colleagues at AMD, ARM, and NVIDIA, and they further illustrate this usage model. They go through them in a lot more details. We will talk about the second usage model after these two slides, next two slides. The second usage model basically deals with UCIe retimers to escape the package using alternate media to construct large scale-up and scale-out systems. We'll see that in 3 slides from now. So here is an example of building a large radix CXL3 switch from multiple smaller radix CXL switch dies of 128 lanes as shown here. Now the single die CXL switch that you see here is for 128 lanes, and that might be the sweet spot from a market deployment, cost, yield point of view. This die has 128 lanes of CXL plus 8 ports of UCIe for enabling to build scale-up system. Now, just because 128 lanes is the sweet spot doesn't mean the market doesn't need larger radix switch. In fact, the market does need larger radix CXL switch for building larger system topologies. And we can solve this by putting 2 of the CXL switch dies together on the same package connected through UCIe as shown here. And now you got a 256 lane switch. Now you can also put 4 of them together so that you can construct a 512 lane CXL switch. They will have some unused, CXL ports like shown here and some unused UCIe ports, but you can turn those power off and not pay the power penalty, and you have a way to basically build your scale up. You can use this to build your scale up kind of switching infrastructure that you need. And the protocol that you send over here most likely is not going to be the CXL protocol, because a lot of for CXL, especially up until you get to CXL3, tree topologies are a must, and doing it this way breaks the tree topology. So this is most likely going to be the switches internal, and also from an efficiency point of view, the switches internal interconnect will get ported over through the through UCIe here. This picture here also is representative of other scale-up architectures such as multi-core CPUs. If you look at, for example, our Intel's Sapphire Rapid CPU, it looks very similar to the arrangement where each die has its cores, DDR, PCI CXL link, and the interconnect is through an advanced package on an interconnect technology that predates UCIe. So this is a very good representative sample, representative example of building scale-up solutions. And I want to acknowledge Nathan for providing this slide. Now, here is another example of a package with 2 compute dies and an accelerator die. Now, the compute dies, they have CHI as their interconnect, and that CHI, is mapped directly onto FDI through UCIe as shown here. Now, here the AMBA CHI is the streaming protocol, which is sent over UCIe, and they use die-to-die adapter to make sure that the reliable delivery mechanism works. Now, the designer might choose that one of the ports, like shown here, is an open slot. In that case, it has to map both CHI and CXL onto the die-to-die adapter. One will be active. So if the other side has CHI, for example, the accelerator, they're going to talk CHI. If it does not, then they will talk through CXL. So in this case, the protocol is both either streaming protocol through CHI or through CXL protocol running over UCIe. So these are some good examples. And again, I want to acknowledge our colleagues that provided this example here. Now, a second usage model. So the first one is to basically package level integration example. A second usage model here is, off-package connectivity through what we call retimers. So they basically connect to another alternate media. So let's look at this example here. One can put an optical chiplet here. This is the example of a CPU package, for example. You can put an optical chiplet here, and that is going to provide you with an optical connectivity. This is co-packaged optics. Optical has the promise of delivering a huge amount of bandwidth that fits really well with the amount of bandwidth you can deliver on package that we are going to see. As a result, you can extend CXL through UCIe to a rack or even at a pod level, right? This is this solves the distance problem. Now let's look at this particular application with UCIe. The picture here basically represents CXL3 as the underlying fabric, and it's used to build a dynamically composable system that can be at the rack level or even at the pod level. This is the physical representation. This is the logical representation on the left side here. You got compute nodes, which are basically individual servers, a pool of accelerators, a pool of storage, a pool of memory that can be either pooled or even shared, connected through an infrastructure processing unit, which in turn connects to the network. I can use co-packaged optics using UCIe retimer from the package as we showed here. That can deliver high bandwidth with low latency and low power while you're solving the reach problem. You can go anywhere within the rack or you can go across the racks. And if by the same token, the switch can be having also the UCIe based optical retimer connecting to the switch die. And this is a scale-up example of the switch going from the 2 slides back. And then here are the CXL ports connecting to pooled memory, shared memory, pooled accelerators, all of those things. So you can build this multiple direct connection to the switching infrastructure from each of these end nodes, so to speak, and basically be able to dynamically assign resources when it is needed, and also use the load store, low latency based coherent shared memory for collaborative problem solving across a huge number of compute clusters, for example, in your HPC applications. So the bottom line is this second usage model of UCIe with retimers can enable us to build composable systems at the data center, which will result in better power efficient performance while reducing the total cost of ownership. And in this context, total cost of ownership is both from a CapEx as well as an OpEx point of view. Now, we talked about these metrics here for UCIe, the frequencies, the weights for each one, the bump pitch ranges, and then the channel reach that is there with each and every one of them. Now let's look into the KPIs here. Now, it should be noted that these numbers, they include everything. The entire file, including circuits, clocking, logic, data serialization, deserialization, sideband, link training, scrambling, lane repair, you name it. It includes the die-to-die adapter, including CRC, retry, and these numbers are for advanced package at 45 micron, very conservatively estimated, and standard at 110 micron. Now, we do expect designs to be in this zip code for the KPIs. Some will do better, For example, in terms of power efficiency and latency, those things, some will do better, some may do worse, but this is the ballpark number. The other thing is that the bandwidth, when we quote, it is in gigabytes per second, not gigabits, gigabytes per second, both for the linear as well as aerial. And the range here that you see is proportionate to the frequency of operation. So if you take this example here on the advanced package, on the bandwidth density for area, you get 188 gigabytes per second per square millimeter at 4 gig. You get 376 gigabyte per second per square millimeter at 8 gig. This is for one cluster. And you get 1350 gigabytes per second per square millimeter, which is close to 1.4 terabytes per second per square millimeter at 32 gig in the advanced package. Now, just for the comparison, the SerDes bandwidth density with PCIe and CXL, it's around 10 gigabytes per second per square millimeter, which is basically we are getting 2 to 3 orders of magnitude better bandwidth density with UCIe. Now, this is expected since on-package channels are much shorter and they're well behaved compared to onboard interconnects. So the circuits are much simpler. We are pretty much bump limited. So if we went down here from, let's say, 45 micron to 25 micron, like the spec allows, we expect this bandwidth density to go up by more than 3x, which is a tremendous amount of bandwidth density. Now, in reality, the numbers that we get even here are pretty good. And I expect people to just dial down the frequency and drive the power efficiency even lower, which is good, to get better and approach on-die level of power. Now, the power efficiency, it's expected to be 0.5 picojoule per bit for standard and 0.25 for advanced. Now, contrast this to what we see, 5 to 10 picojoule per bit in an external interconnect. And again, we expect these numbers to get significantly better as the technology evolves because the bump pitches will shrink, the distance will go down. So things will start getting even better going forward, right? And again, this is expected because these links are much well behaved. Now, while power efficiency is important, it's critical to get into and out of low power state. We expect to save about 85% of power with a transition time of either 0.5 or less than a nanosecond. Now, that means that the physical layer can autonomously decide to save power as needed, right? 2 gigahertz, if you assume is an internal frequency, basically every clock cycle, you can make a decision whether to turn things on or off, right? And that means that you get this power savings. And practically, the important thing is you get to a linear power bandwidth consumption load line with this interconnect. So recall that I said if I consume 10% of the power, I should be 10% of the bandwidth, I should be consuming 10% of the power. This enables us to get there. And you cannot really achieve this level of power savings with external interconnect because the entry and exit latencies there are several microseconds. Again, this is the nature of the interconnect. There is nothing you can do there. Now, the latency for TX plus RX is less than 2 nanoseconds. And again, an order of magnitude less than the external interconnects. Reliability is measured in FIT, which is failure in time. Now, how many failures you get in a billion hours? We expect less than 10 to the power minus 10 failures over a billion hours. So practically, this link is very robust. Now, in summary, UCIe 1.0, it delivers the best performance metrics while meeting the projected needs for the next 5 to 6 years across different segments of compute. Now, an open industry standard body defining a specification with compelling KPIs that caters to a wide range of usages and that has a comprehensive compliance and interoperability mechanism is essential to develop a healthy ecosystem. As we saw, UCIe has all of those attributes. On-package integration of dies has matured as a technology across the industry, covering manufacturing, assembly, test companies. We see compelling products already being offered from multiple foundries, as well as through OSATs in the marketplace using proprietary interconnects for scale-ups like we talked about. And what is important is several vendors have already announced the availability of IPs and VIPs with UCIe. So in summary, we basically need a predictable path to design compliance with UCIe, and we are there. Now, in summary, UCIe Consortium got formed last year, got incorporated. It's an open industry standard that establishes an open chiplet ecosystem. There is tremendous support in the industry. This is poised to be the way SoCs get built. The specification 1.0 specification is available for the public in this website. There was a question on that. And again, we are an open consortium. We welcome all interested companies and institutions, if they have not joined us, to join us. There are 5 technical work groups: electrical, protocol, form factor, compliance, manageability, security, systems and software. We also have marketing work group that's basically responsible for driving the technology forward. There is plenty of innovations happening in the consortium. I am very, very excited. And we are on a great path with UCIe. And I see similar or probably higher excitement to how CXL evolved, which I was involved in from the beginning. I'm very confident that UCIe will be widely deployed, and we will all be designing SoCs using UCIe. Thank you very much. Now let's get to some questions. All UCIe questions, whether we answer them today or not, will be addressed in one or multiple blocks going forward. Stay tuned. So Gerald, let's see what questions we have here.
Great. Can you hear me, Debendra?
I can hear you.
Fantastic. Thank you, Debendra, for the presentation. So let me try to summarize questions and try to hit often asked questions as well as questions that came up here. So one of them is, the spec has comprehensive explanations of how to build the adapter for PCIe and CXL. When can we expect to see similar specifications, explanations for other widely used protocols?
It's a good question. As we had talked about, we have mapped the streaming protocols, and you saw an example of AXI Chai to UCIe through the die-to-die adapter. So it's already happening, and stay tuned for more.
Very good. Another question, this one's electrical related. Are there any plans to expand data rates beyond what is supported in the spec today, intermediate frequencies and or lower and higher than what is in the specification today?
Good question, Gerald. Let me see. So intermediate, by that I mean, I'm assuming they mean, we support 4, 8, 12, 16, 24, 32. Would we support something in between? And then, of course, would we go below 4 and above 32? I'm assuming that's the question. So now, as you can see, we already have non-power of 2 data rates, right? 12 and 24. Now, in the end, it's a trade-off between validation, how much validation you want to do for the intermediate data rates. I think right now we have the right mix in terms of going from 4 to 32. Now, the other interesting question is lower or the higher data rates. And today we have extremely high bandwidth density. And in the future, as the bump, so the question is, do we want to go above 32? We can always go above 32. The challenge is keeping such a low power efficiency number. So I see that in the future, the bump pitches will go lower. In that case, naturally, the direction might be to go for the lower data rate, as we had talked about, effectively wider. And that will be beneficial while delivering a high bandwidth. That is also beneficial from a power efficiency, latency, all of that point of view. But certainly we can, and we will look into the higher data rates if an application poses itself for those kind of things. We know how to do it. It's just a question of, is there value add in doing it?
Okay, thank you. Another question regarding overhead pins like sideband, which we have a couple of per direction per PHY module. In terms of, can you comment on the criticality of sideband, of including it in the PHY itself, as well as the impact to KPIs?
Okay. So sideband functionality is extremely critical for any open standard interconnect. Now, the sideband, if you look at it, is used for things like link training, debug, manageability. People have talked about using it for things like firmware update because it's a very high bandwidth on 800 mega transfers per second, which we have provided. It's in an always-on voltage domain. Now, all external interconnects, for example, like PCI Express, they have a sideband. Why do you need a sideband? First of all, for example, if your link is hung, you don't want to come through the main band and try to debug it. You have to go through the sideband, right? So The lack of a sideband effectively in the other standards that we did, standardized sideband has caused people to it's not that they don't deploy the sideband, they just went with proprietary solutions. And that's the learning, right? I mean, the part of the learning of these being over 2 decades, right? And PCI Express and other things is that you learn what you should have done right from the beginning. We don't want to do the same thing. We want to avoid that in UCIe. So given that sideband is essential, we define the sideband. Now let's talk about the overhead. Now, if you look at the bump map, you will notice that we place the sideband by depopulating some of the VSS pads. So there is no shoreline penalty. Most people will route these signals in the backside of the package layer, so there is no critical routing issues that are expected. And by the way, the area and power KPIs, all of those, as I mentioned during the presentation, they already included the sidebands, and we still have very compelling KPIs. So yes, basic thing is that you got to define things that you need, and you need to move forward so that everybody is doing things the same way.
Okay, thank you. And another question here, and there's questions coming in fast and furious. And just as a reminder, as Debendra mentioned, we're not going to get to all of them. So we will have a series of blog posts upcoming, and we will make sure to answer all of the UCIe related questions that came up here. Next question, Debendra, does UCIe support 3D stacking die-to-die configurations? And if not, what is the timeline or plan for this in the future?
The initial UCIe 1.0 specification, it covers 2D and 2.5D, 2.5D, which is the advanced package that we said. It does not include 3D in the 1.0 specification. But having said that, even when we announced the consortium, we said that we do plan to support 3D. It's a very compelling usage model. Personally, I'm very excited about it, and we will release it in a future revision of the specification. So absolutely, 3D will be covered in UCIe in a future rev of the spec. Please stay tuned.
Okay, thank you. And let me get to the next question here. Regarding flit sizing, if I use a 68-byte flit, and if I don't have anything beyond it, how do I handle this? Debendra, I'm not sure. Does that make sense? I'm trying to understand the question fully myself.
I think I understand what is the intent of the question. Basically, it means that, hey, 68-byte flit, right? So it's not a multiple of 16 lanes or 64 lanes that we have on on the advanced package, right? So it's not a multiple. So if I have a flit that ends halfway through, let's say it ends in lane number 3, what do I do and I have no other flit to send. What do I do? I think there was a picture where I showed the next flit was continuing. What if it ends in lane number 3 and I don't have anything to send? Well, in that particular case, that header will say that, hey, there is nothing there, and you're going to 0 extend the flit. I think that was the question. So yes, we have thought about that. We have comprehended it.
Okay, thank you. Let me try to see if I can get a couple more questions in here. Next one, does UCIe support RDL/fan-out packaging technology usages? They are popular amongst OSAT offerings, multiple OSAT offerings. So can you comment on RDL and fan-out technology?
Yes. That falls into the category of UCIe advanced, and the 3 examples I gave were, like I said, representative samples, but there are others. So this is one of those. And we support the 25 to 55 micron bump pitch range, and it's expected to work with RDL fan-out technologies with sufficient number of routing layers, depending on the routing pitch of that technology. That we give a wide range, 25 to 55, so it should work.
Excellent. Let's see if we can fit one more question in here. Today, UCIe only supports 2-layer and 4-layer package routing. Are there any plans for 1 and 3-layer support for finer granularity cost optimization?
Now, UCIe S has been optimized for bandwidth per millimeter and bandwidth per square millimeter for a wide variety of use cases, and we allowed a wide combination of data rate support. We do 2-layer and 4-layer supporting. We believe this is enough for a wide cross range of sections while reasonably containing the combinations to a manageable number for guaranteed interop. So, no immediate plans for 1 and 3. We at this point we just don't see the need. But again, if there is a need, we are always there to address it.
Excellent. Thank you, Debendra. There's more questions, as we mentioned. We will get to them in blog posts. But back to you. I think we're pretty much out of time as well. So thank you.
Yes, thank you, Debendra and Gerald, for sharing your expertise. Being mindful of the time here, we will wrap up today's webinar. The presentation slides and the webinar recording will be available on the UCIe Consortium website. As we mentioned, we will be addressing all the questions we received today that we weren't able to address in the live webinar in a future blog. So please follow the UCIe Consortium on Twitter and LinkedIn for updates. Once again, we would like to thank you for attending the Introduction to UCIe webinar.